Hello, guys. Troops, as Victor Williamson would always call the members of the Space Center staff. So this video here is my video on how to properly design a starship, a star system using the proper science and things like that. So what I'm going to be doing today is sharing from some presentations that I've made over the years, taking here and there as needed. The goal today is to help you understand the science of stars and how solar systems form so that you have an idea of what you can and cannot do, and also what rules you can break to make things extra strange. So we're going to be pulling from a couple of PowerPoints. The first one that I'm going to do is I'm going to go just over stars themselves, because that'll be important. And then I want to talk about the spreadsheet that we have that will let you place your planets intelligently so that you don't have any systems that are going to destroy themselves. Also, so that you don't have life in systems where it would never evolve. And you may think, well, why put limits on it at all? Well, it's actually by understanding the limits, the limits will help you write and come up with unique systems that you never would have thought of before. By knowing the limits, you'll know what depths you can explore, and as you ask questions and say, well, a real system would do this, you can start to say why, and then that'll lead you down to interesting paths that you hadn't thought of before. There you go. Okay. For instance, one limitation you might find is, well, a life cannot evolve around a big blue star because there's just not enough time for it to emerge. So if there is life there, then okay, we're defying that rule. Why is there life there after all? How did it end up there? And by answering that question, you have made a very interesting and unique system. So I don't want you to think of all these rules as like limitations. I want you to think of them as like writing prompts. And I also want you to use this to sort of understand how likely and what probability such things should occur. So we don't have life under every rock and corner, Okay, I want to get quickly on this. We're already 3 minutes in, so let's get cracking, shall we? So when you're designing a solar system, it all starts with the star. No surprise there, I'm sure, but yes, it is all about the star. The first thing you need to pick is your star, and once you do that, things start to fall into place. So what kind of star should we pick? What options are there? All that kind of stuff. We're going to start with that first. And then once we understand our options, we'll talk planets, where they can be, and what they need to be in order to have certain characteristics. All right, let's talk stars. Now, I'm not going to talk a lot about... wait a minute. It's not the right screen. I'll just have to talk about it here. Okay, so stars. Why do they burn? They're actually big giant hydrogen bombs going off constantly. And hydrogen is different than nuclear bombs. They're hydrogen bombs, but they're different. There's atom bombs and hydrogen bombs. Hydrogen bombs are the fusion type. This is what the sun is doing. The sun is producing new elements constantly by taking molecules and merging them together into a bigger molecule. And doing this produces energy. Not all of the mass converts into the new mass. Some of it is converted directly into energy. So this little ball here actually weighs less than the stuff that joined together. And the stuff that is missing is converted into energy, and that's what makes the big booms and the big suns. So that this right here is a gravitationally controlled hydrogen bomb runaway. So I won't go in much into it beyond that. But as we start to go into properties of the stars, look at this picture here, and I want you to say, what do you notice here? There's three things that I notice that are different across this wall of stars. Number one, the most obvious, is color. These stars are different colors. They're not all kinds of random colors, like you're not going to go out there and find purple stars and green stars, but you will find red, orange, yellows, and whites and blues. So the color is a big thing, but not as big as you might think. And then there's brightness, how bright is the star, and then it's mass. And the big one in this is going to be the mass. The mass will determine a lot of these things over here. Not necessarily, but it has a big effect on it. So if we go into, and by the way, talking of mass, whenever we're talking about other suns beside ourselves, instead of saying how big it is in kilometers or meters, which are numbers that are so massive that it just doesn't even matter, you just can't even imagine it. So what we always do is we imagine our stars in terms of like in relation to the sun. So this star's mass is 2 suns, 3 suns, 1.86 suns, 0.124 suns, and it has a radius of 0.5 suns. Otherwise it just has no meaning. Same thing with how its brightness. Those three things that I was talking about before: brightness, color. Really, brightness is luminosity, and color is tied to temperature. So we're really talking luminosity, temperature, and mass. So as you come down here, then again, you'll see that this one has a mass of 0.3 suns and a 4/100ths of the luminosity, the brightness of the sun, and it only has 11/100ths of the radius of the sun, kind of thing. Otherwise, we're stuck using giant scientific notations. Like, look at this number over here. The sun has a mass of 2 with 30 zeros behind it in kilograms. Like, we don't want to deal with those numbers. Okay, so keep in mind we got 3 properties that you're going to want to look at: mass, brightness, and the temperature. Okay, so now how we've classified stars actually came from a bunch of women astronomers in Harvard, which was really cool. And they were the ones that came up with the star classes. The one that came up with them, her name was Annie Jump Cannon, and she decided that we should classify stars by their temperature. And when they did that, the old system of ordering them by their strength of their hydrogen spectrum line, that kind of went away, and they fell into a really weird line of letters. So this letters, it may look like it's really random, but it's just the leftovers of an old classification system. And remember, they were classifying hundreds and thousands of stars on paper by hand, so I'm sure it was not convenient for them to go back and reclassify them once they had a new classification system. So that's why they hold to this system, and it's the OBAFGKM system. The O being the hottest, biggest, brightest stars, and the M's being the smallest, dimmest ones. And you can kind of get a feel for what their temperatures and colors are from this slide. You can also get an idea of their sizes based on this as well. The sun is a G-type star. Okay, so the really, really big ones, O's, and the really tiny ones, the M's. Now, if you're trying to remember what the classifications are, here's your mnemonic device. It's O, be a fine girl, guy, kiss me, which Annie Jump Cannon came up with. I'm sure just trying to come up with something. But yeah, so that's what it is. Oh, be a fine girl, kiss me. Oh, be a fine guy, kiss me, something. But those are the star classes. So as you're designing systems, you're really going to want to get to know this. Because once you know the class, you should have a general idea of whether it's possible to have life, what kind of planets there's going to be, and what kind of systems can I have. It really falls into what these are, and how often can I make one of these. Okay, let's talk a little bit about temperature then, and why is color and temperature linked? Well, I won't get it too far into this. This is a lot of science stuff. That is not important when you're designing star systems necessarily, but it could give you some ideas. For instance, all objects, well, they glow in a certain light range frequency based on their temperature, because atoms are atoms jiggle, and they jiggle faster the hotter they are. In fact, temperature is just measuring how much your atoms are jiggling. And light is produced whenever an atom jiggles. So every object is literally glowing as if it is a fire or a flame in and of itself. It's not like it's... Most of the stuff that we see is reflecting light, but it's also actually emitting light. And the light frequencies that it emits depends on how fast those molecules are jiggling. The more rapid jiggles produce higher energy light. So humans right here, we are about 310 kelvins. That's our temperature. So we emit light over on these wavelengths. This is the infrared wavelength range, which is why infrared goggles can see in the dark, because they're able to see people's glow. Well, the sun is this line right here. It's about 5,800 Kelvin, and it's glowing. It's so hot that it's glowing in these frequencies. Well, it just so happens that our eyes are attuned to the frequencies that it emits the most intensely. That's what this curve is here. It shows what the wavelength that the sun is emitting, and then how intense, how bright those frequencies are. So the sun is the most intense on these frequencies. And that's really not a coincidence that the visible light spectrum matches our sun's most bright light, because that's what our eyes would have evolved to see, because that's the light we had to work with, so we evolved to be able to use it. Now, why do I bring this in? Because if you're designing a different star system, you might have a 3,000 Kelvin star like this, okay? Well, the frequencies that it emits the most brightly are here, light that we can't even see. It's in the infrared spectrum. So any life that evolved there would evolve to see different light than we would. They would not see the things that we see, or they would, but they would be very dimly blue to them, because they don't see these frequencies. They're seeing these frequencies. Things that we see as glowing red, they can't even see it. And things that we can't see because it's in the infrared, they would see very clearly. So it would make for some different aliens, and they would literally see the world differently than we do. That's the only reason I bring that in, is so that you can see some of the ramifications of choosing your star. The plants that are going to evolve under this 3,000 Kelvin star are going to evolve to be green for these, right? And they're going to be absorbing all the other colors. So our visible light, our red, would fall on the foliage there and just be absorbed. And maybe the plants are reflecting mostly these frequencies, but a little bit of these. So they would appear very dark red to us, the plants on these worlds. So do you see how understanding the science of the star kind of creates worlds that you may not have ever thought of before? These worlds with dim stars and dark red plants, stuff like that. And the skies would be different colors too. You see, our sky on Earth is blue because these frequencies right here, the ones that we see as blue, hit the oxygen atmosphere and scatter all over the place. Well, on an alien world, if they have oxygen, yeah, the blue would be scattered, but there's not as much. See how it's like 100 times less as intense as the blue light of our sun, or more. So those skies are not going to have very much blue. They're going to be mostly black. It's just going to be like a very dim blue to us. Now, to aliens living there, their skies might be completely black because they can't even see those lights that are reflected. They would just look up and see the stars in the middle of the day. It'd be kind of weird, right? To look around, have the bright worlds around you, but you look up at the sky and you can see the stars with the giant sun in the middle of it glowing. So there's all kinds of interesting stuff that happens just based on the fact that your star has a different temperature, and so life would evolve to mess with those frequencies, not ours. And if you're like, well, I can't even keep all that in track, just think, okay, anything red for us is blue to them. Anything green to them is red for us. Kind of stuff. It shifts that way. We can go more over this later. But yeah, anything that is blue to them, that's red for us. Anything red for us is blue to them. Anything red to them, we can't even see. Yeah, that kind of stuff. And blue stuff for us, they can't see. Or it's just black, you know. All right, so I think that's enough about that. Now, if you plot all of the stars based on their temperature, they roll out like this. So here is their brightness, and here's their temperature. And if you plot them, they fall along this general line, with a bunch of them up here, and a bunch of them way down here, and that's about it. So they're going to fall somewhere in one of these three zones, unless they're an odd one up here. And those can happen, but they're very rare. You're not going to go out and make like 80 of them in the solar system or in the galaxy, because that's so rare. And these locations actually also indicate the life patterns of the stars. And so the thing that you're going to want to look at is this Roman numeral right here. See, 5 are main sequence. Those are regular stars in the middle part of their lifetime. And then you got these 4 for subgiants, 3 for giants, 2 for bright giants, and then up here these 1s. Those are supergiants, the megastars. And as you can see, most of the stars are on the main sequence and in the class 3-4 range. This is where most stars live, because this is where the life cycle of stars really takes place. And in general, what happens is a star forms, it lives its life, and then as it dies, it starts to migrate up this path up into the giant stage. And then it either then dies there and drops down into be a white dwarf, or it becomes a supernova and just obliterates itself. Or maybe leaving a neutron star or a black hole. Yeah, we can. Let me go over that again. Stars are born onto the main sequence, and they live most of their life here. As they die, they become these 4 and 3 giants, and then when they run out of fuel and truly are dead, they either leave behind white dwarfs if they're small, or they explode in supernova and leave black holes if they're big. But 90% of the stars are going to be one of these. Up here you can see the classes as they're mapped with the letters as well. O stars are odd, are very rare. Okay, here's another picture of it where you can see, okay, stars are living along the main sequence, and as they start to die, yeah, they end up there. Okay, we are 18 minutes in. Yeah, you can see it here. They live here, and then as they start to die, they bleed off here and become these, and then either die down to white dwarfs or in supernova. Okay, with that being said, I think... Oh, how common are the types of stars? So 90% of all the stars are on the main sequence. But then how many red ones are there? Yellow, orange, white, blues. But that's what we want to talk about next. Let's talk this. So, as you look at the abundance of all of the types of stars around us, you'll notice that most of the stars are all M-class stars, the little itty-bitty ones. And then there's more with K, and then G where the sun is, and then F, and there's not really many A's by the time you get there. And there are no B's or O's. There's a very good reason for this. the vast majority of stars are M-class little red dwarfs. Vast majority. We're talking like 70%. So most of the stars that you make need to reflect this. Okay, we can't have a million A's and O's because they're interesting, and have it be so unrealistic because there's not enough M's to balance them out. And if you look at our solar neighborhood, again, this way, you'll see that these stars, as they fall on this HR diagram here, they go back with the white dwarfs. There's a bunch of white dwarfs in there, and then you've got a few yellows, a few oranges, and a million reds. One white and one blue, and that's it. Okay, so that kind of shows you the star classes, how they're tied to temperatures, and their abundance. Okay. So now I want to talk about some of the ramifications of these stars, and how they live. So I'm going to go now into the life cycle of stars, and I'll do this fairly quickly. Okay, so how stars live and die is they're always, what makes the star a big ball of fire is you've got this explosion in the middle from the fusion, and then you've also have the rest of the material that yeah, does that make sense? So the explosion pushes out, the gravity of the star pushes in, and the star is at a balance of these two forces. And if that battle ever gets out of balance, that's when the star changes. Okay. So here is a star here that has died. So is this one. So it is possible to, so we have seen dead stars all over the place. So it's always a fight between the outward explosion force and the inward pressure of the gravity. So as stars live, first they start in a big cloud of dust, and then that dust starts to condense and clump. And if you look at this Eagle's Nebula warp cloud, so then as the dust comes together, it forms little clumps, and inside of these is where stars are born. So these stars, how they form from these little clumps is you have a little clump that starts to shrink as it collapses due to its own gravity. And as it shrinks, the center of the stuff begins to heat up. It also flattens into a disk. Yeah, you can see these little clumps inside the pillar. Oh man. Yeah, so it starts to shrink as it collapses, and that's why the solar system is like a disk. It just flattens as it collapses and spins. As it collapses, it has to spin faster and faster to maintain its momentum, and doing that stretches the material out into a thin disk. And it starts to heat up in the middle, making it a protostar. So protostars are here, and here's where all the planets are formed from. And we have photos of these protostars in nebulas, so we think we're pretty good. Okay, so there's the protostars. Okay. Okay. Let's see. Blah, blah, blah. Well, this does not have what I wanted in it. Where is it? Might be in a new presentation. So I want to talk a little bit more about the life of a star. But to summarize, it's always a fight between the outward explosion and the inward pressure of gravity. And as it runs out of fuel, that those pressures change, and that's what causes the star to die. If it doesn't have enough fuel anymore, everything will just collapse in. Yeah, and that's where the big supernova is. Okay, that's not what I wanted. Let's try this. Oh yeah, okay. So once again, here's our stellar neighborhood, and look how many red stars we have around us. And then just a couple of yellows, and then a bunch of oranges, and only one blue and only one white. And that's not, there's no B's or O's either. So why is it so boring? Why is it that we only have mostly red stars? So the reason why we only have red stars is because red stars live forever. And O and B stars barely live at all. So whenever they're formed, all the red stars that have ever formed are still here with us. And most of the blues that formed died a long time ago. So that's why we don't really have any of them. They blew up forever ago. Okay? You see, O and B stars, they only live a few million years. This is a star-forming region in a different galaxy. And look how many blue and orange stars there are in there. So early on, there were tons of them. But then they only lived for a few million years, so they blew up really quickly. And then their explosions, though, are what produced all of the heavy elements that we enjoy on our planet today, like gold, platinum, and the others above iron. So our neighborhood, our solar system, probably did look something like this several 100 million years ago, when the blue stars were around to create the heavy elements for ours. Yeah, let's see. Let's see. Okay, so there you go. Let's kind of start wrapping this up so I can show you the spreadsheet that you'll use for this. But I do need you to understand this basic science, okay? So yeah, the idea is that if you, depending on which class of star you choose, you know, O and B live for very few years. The A stars also don't live very long. You know, we're talking 500 million to 1 billion years. And F stars as well, they maybe live 2 or 3 billion years. Whereas G stars like the Sun are 10 billion. These are like 30 or to 50 or more billion. These guys can live trillions of years. And if the universe is only 13.6 billion years old, there hasn't been enough time for all of the M-class stars that were formed to have died. So that's why there's more of these than anything else. Yeah, so that's why most of the stars are M's. Okay, so this is just all about planet formation. This is a lot about how our planet forms. So you have your star, and you've got other stuff around it, right? The star forms from a big dusty ring in the protostar, right? So the star forms in the middle, and the planets form outside. The planets actually form first before the sun officially does. Which is a little surprising, but they do. They form in the first 10 million to 100 million years. But it takes tens of millions of years for the fusion to actually start inside the star. Okay, so how do planets form? Well, you see, the protostar is hot in the middle, but it cools off as it goes out. So there's regions where ice will melt, but beyond it freezes, and so on and so forth. So what happens is you form these little lines. So here's a line right here where ice forms. And then here's a line where rocks melt. And then here's a line where you get like frozen CO2 and stuff like that. And the planets start to form because where that freezing line is, stuff starts to clump there. And that's where the planets actually form. But it also creates a period of terrible bombardment, because as your planets are forming in these rocky areas, they just get the crap kicked out of them. But the planets have to form before the star, because once the star forms, all of that dust, the stuff that isn't used by the planets, it gets blown away by the solar wind. So like you've got this planet here, and the sun forms, all the dust that it was forming from anything left over that's not like rock size gets blown away. So that's where the planets form. You get a rock line where rocks freeze from lava to solid rock so they can make rocks. And then you've got the snow line where ice freezes, and then you have the carbon freeze line. So that's kind of where you can expect your planets to form. If you have something beyond the snow line, you're not going to have liquid water, anything like that. But yeah, from that, so early planets are going to have the snot kicked out of them, right? And it takes them, anywhere from 10 to 100 million years to form. So why do I tell you that? Well, because if you pick an O or a B star, these guys die depending on how big it is. The really big ones maybe live only 3 billion years and then they blow up. How are you going to form a planet around that? You won't. So you don't get planets around O and B stars. They die before the planets finish forming. And what's left gets blown away by a supernova anyway. So if you have an O star, don't expect to have planets. Or here's an opportunity where you could have a planet there and then it's weird. And you have to explain, how did it get there? Was it a rogue planet that had been flung off a long time ago and captured by this O star? And it has just a few million years to live before it gets blown away. So there's some opportunities. And then would you have life around an O or a B star? Life takes, we think life didn't start forming on Earth for 500 million years. This maybe starting about 4 billion years ago. And it didn't form life as we know it until really in the last 500 million years. So it took about 3.5 billion years for life to evolve into anything besides bacteria and plants. So if you have a star that doesn't live long enough for life to form, you're not going to have life. So you're going to be stuck with life only around maybe the coolest F stars. You'll have it around G stars, obviously, because our sun is the G star. You'll definitely have it for Ks and maybe Ms. But there's problems with M's we're finding as well. So really, if you're going to have life, it's going to be relegated to the G and especially the K. Some scientists think the K is perfect stars, and maybe a cool F, maybe. But definitely not A, B, O, or M. And we'll get to that. So this is why you need to know the rules. If you choose an M star, you probably can rule out life, and you can start to think about a different kind of star. If you choose an A star, you're going to rule out life, but you'll still have planets. B or O ain't going to have anything. Okay. Although these big stars, they do tend to form binary companions. So you can have a lot of binary stars with these upper ones. But you can have binary stars for everywhere. Anyway, now planet formation, as far as planets go, should you have a gas giant? There's 3 different classes of planets, as we know. There's rocky ones, there's gas giants, and then there's ice giants. So gas giants are Jupiter, Uranus and Neptune are ice giants. And then you have Earth, which is an example of rocky planets, okay? We're going to get into that a little bit with a different PowerPoint. So let's see, planets we don't know here. Because now we understand a little bit about the stars. We've got the O, B, A, F, G, K, M stars. Planets don't form for O and B. Life only evolves for the coolest F stars, G stars, and K stars. So those are some of our main limits. Now, as we look at the planets, what kind of planets can we choose? Well, here's what the numbers show. And you can pause this and kind of look at it and reference it. Less than 1% of systems with hot giants. So what is a hot giant? A hot giant is a Jupiter that orbits really, really closely to the star. Like we're talking has an orbit of hours or just a few days. So less than 1% of them are like that. 1 to 5% of the systems, really massive and metal-rich stars, will have warm giants, so, and occasionally with small planets on very close orbits. And again, that would be A and F stars. So if you have an A or an F star, you're probably going to have some gas giants and a few small ones. 5% of the systems, very mostly massive and metal-rich, will have highly eccentric gas giants and few or no other planets. And the reason for that is the eccentric giants would have killed off any of the others. Another 5 to 10% will be massive and metal-rich. Will have cold giants like our Jupiter, and rarely will they have more than one large one. And then they'll have inner planets with maybe outer ice giants or super Earths. Super Earths are rocky worlds bigger than Earth. Another 5 to 10%, these are lighter stars with large numbers of small planets, with super Earths of similar size tightly packed into the inner system in resonant chains, occasionally with an outer giant, very rarely. So you may have heard of the TRAPPIST-1 system. So the TRAPPIST-1 system is one where there's 7 planets, and they're all like as close as Mercury or closer. How do you have 7 planets that close? Well, it's one of these. Okay, then the vast majority of these light and metal poor stars will have no gas giants and small and super Earth planets. And then another 10 to 40% will be the really metal poor or very massive stars without large planets, but there will be something in orbit. So what I'm saying here is, this is a lot of info. The idea is this. Your star can be massive or have a lot of metal, or both, or neither. So it can have mass and a lot of metal. Yeah, it either has mass, high mass or low mass, or high metallicity and low metallicity. And those give you 4 combinations. Okay? So if you have very massive stars and you have very little metal, you're not going to get a lot of planets at all, and you'll get a few gas giants there. If it's really low mass, like the M stars, and low metallicity, you get lots of planets, no gas giants. Look at that. If it's very light and very metallic, then you'll get some. But notice, I want you to notice how few gas giants there are. So gas giants are actually rare. It's mostly rocky worlds, and in fact, it's mostly super Earths. And if you have high mass and high metallicity, only then does the ratio of gas giants to rocky worlds start to match. So it would appear that our sun, I don't know from this diagram if that indicates the sun, but ours is not a very massive star, but it has enough metal in it that we did get gas giants.
Dad.
There's my daughter.
Why is the star in the middle?
Oh yeah, I was just wondering that myself. This might be Sol, our star, right here. So in other words, are you more massive than the sun? You're over here. And if you have a lot of metal, you'll have you'll have worlds, but not very often, and you'll have a lot of gas giants. And if you're lower in metal, then you'll mostly just have rocky planets. So every star system probably should have planets unless it's an O and a B. Okay, but if you're more massive than the sun, that's when you have a more likelihood of having gas giants. And if you're more massive and more metallic, then you'll have a lot of them. If you're more massive, less metallic, you won't have a lot of gas giants. So mostly pick rocky worlds and super Earths and ice giants like Neptune. And if you're less massive than the sun and have more metallicity, again, very rarely put in giants. And these are just guides, right? These are just ways for you as you're making like hundreds of these stars. Like your mind goes numb unless you have some guideline, right? Okay, now let's look at the kinds of orbits. I know this is a lot, but this is the training for you to learn star systems. And I hope you're taking notes, and you're going to have to watch it more than once. Okay, so here's places in the orbits. Okay, there's something called a Roche line. Then there's a rock line, ice line, hydrocarbon line. Now we've talked about these three things already. This is where rock freezes. Inside of this line, it gets lava-like. So if you're inside here, you're going to have a lava world. Okay, if you're between here and here, you're going to be a rocky world. If you're between here and here, you're going to either be an ice world, or you'll be like Jupiter and Saturn, where you're mostly a gas giant. And if you're beyond the hydrocarbon line, that's when you have like frozen methane, and that's what like Neptune and Uranus are like. The Roche line is a line where you're so close to the star that the tidal forces are stronger than your own gravity. And so the tidal forces from the star that you're orbiting breaks you apart, and you just become a bunch of debris. Planets have Roche lines too. Saturn. This is why Saturn has rings. At some point, a moon got too close. They got within the Roche line of Saturn, and the tidal forces of Saturn were greater than the moon's gravity, and so it broke apart and just spread out to form these rings. And that's why most of the gas giants have rings, because they have a lot of moons, and the odds are of one moon getting in there is pretty high. So all the gas giants actually have rings. Saturn's is just the most pronounced. So you got to watch out for that Roche line when you're placing planets. If you got to keep them outside of that unless you want them to fall apart and break apart, which might be a cool world, might be a cool system to have like a really close like bunch of lava-like rocks going around this star because they're inside the Roche line. Because the Roche line is inside the rock line for stars as well. What is the Hill radius? So a Hill radius is like how close you can put planets to planets. If you're inside the Hill radius, and it has this formula, don't worry about learning formulas. Inside the Hill radius, the planets are too close, and the likelihood is that they're going to destabilize each other, and the solar system won't last for very long, just a few million years before the planets go flying away. So you can't have life on worlds that have these sorts of things. There are exceptions. All right, let's talk about types of orbits. Okay. Now here's one of Kepler's laws where it relates how the period of the orbit, how long it takes to go around once, versus the radius away from the planet. And all these are constants. But this is the distance from the star, and this is how much time passes per orbit. This is the relationship. So the further out you are, the longer it takes, but not at a linear rate. So the further out, it grows more exponentially. So for instance, like Mercury's year is 1/4 that of Earth, and it's a third its distance to the sun is 1/3 the distance to Earth. But if you go out to Jupiter only 5 times further than ours, it's like 45 years orbit. It's so the length of the orbit is much more pronounced as the further out you go. So, but there's some other things that you can have. You can have something called a resonant orbit. So a resonant orbit is where you have like this thing goes around the sun 3 times, and the one outside goes around 2 times, and it's perfect, like clockwork. This is actually very common in asteroids and moons. You can have co-orbital planets. So you can have planets where so you've got like planets that orbit each other and then orbit the star. That would be kind of a cool idea. Pluto is one of these. So one of the reasons why we don't think of Pluto as a planet is because its moon is almost as big as Pluto. And so instead of the moon going around Pluto, the Pluto and the moon kind of go around each other. You can have something called a Lagrange orbit. So if you think of having like a circle, so here's the orbit of
Hi, beautiful girl. You want to come upstairs?
the star, and then here's a planet. There's going to be points on these orbits like this, where if a planet is here, or here, or here, even though they have the same radius, they won't destabilize each other. Because the gravity pull this way, or I should say like this, and the gravity pull this way, they balance out. And that happens at these 3 points. So these are stable and these are stable. There's also another one out here, and this is so these make up the 1, 2, 3, 4, and I think there's another one there. These are the 5 Lagrange points in orbits. And these points, what happens here and here is like the gravity pull in from both objects is such that it will have the same speed radially. So as if like the time for this to go around is the same as the time for this to go around. Is that making sense? Like this planet will have a year of 1 year, and so will this one. And they're actually much closer than I've drawn them. This point right here is where the James Webb Telescope is. So it's 1 million miles from Earth, but it still has an orbit of 1 year because it's in that Lagrange point. And I think there's a Lagrange point there too. But planets, it's probably hard to find planets in these Lagrange points. These are actually not very stable ones, I think. But you could find them at these points, I think. And you may do a little more research in that. Tadpole orbits I may go into in a different time. You can look these up. Tadpole orbits are they're kind of funky, where it's like they kind of orbit like this or something like that because of, I forget. And it's basically because the orbit of the sun and the other planet kind of destabilize it, morphing it from a circle to a tadpole shape back to a circle. So that could be kind of odd. And then a quasi-satellite is one where it's like far like this and it's kind of orbiting like both. I think they do this. That's the orbit. Something like that. You could look into that more. These are for co-orbital planets. Planets that have the same distance. These are the ones that violate the Hill radius. So, like I said before, you have to match the Hill radius or you'll be unstable, except if you're a co-orbital planet. So you can be a binary, you can be in a Lagrange point. You can also, these ones also, right here, the resonant orbits, they can violate the Hill radius. This is how you got 1 million planets close in the TRAPPIST system. They're all very resonant with each other. Okay, so the other type of orbit that you can have for planets are tidal orbits. These are orbits where they're so close that the sun has exerted so much tidal force on it that they no longer spin. I mean, they spin, but the time it takes to spin is the same time it takes to go around the whole sun. So, therefore, the same side of the planet is always facing the sun, and the same side of the planet is always facing away. So, the sun only changes location in the sky based on how you travel. If you want to see the sun set, you have to go north or south or east or west, instead of just waiting around like it is on Earth. And if you went to the place where the sun was setting, it would always be setting. It would never change position in the sky. and the other side is always in nighttime. So you'd have very hot, deserty sides of the planet. I've also seen others where it's like, if there's water, if there's ocean on the planet, then you're going to have like an eternal hurricane on the side that's facing the star. And then it's always going to be ice and ice age and dark on the other side. So that's tidal orbits. And it may only be nice to live along the band where it's eternally sunset or sunrise, or a little closer in, where it's pleasant. So that would make for worlds where the real estate is very is a little more interesting. You get worlds, yeah, and you can have worlds that are too hot, worlds that are too cold, and find ways to live in them. For instance, like you could have a habitable moon around a planet, around a big gas giant that's far from the sun. So the surface of this planet is ice, but underneath, because of the tidal heating from the big gas giant, the water is liquid. So you could have like fish people living underwater, or just fish animals, or you could have space stations underwater, in these worlds where it's liquid. And you could have desert worlds where so they live up on the polar ice cap. That's the only place where it's livable. Okay, elliptical orbits are your standard orbits. This is the kind that every planet on Earth in the solar system has. These are just orbits that are... no orbit is actually a circle. They're always ellipses like this, and the star is at one point over here. And so this leads you to something called the periapsis. Periapsis. And this right here is known as apoapsis. Okay? All planets have elliptical orbits like this, and they have a periapsis and apoapsis. For our solar system, most of them are nearly circular. So how circular is something? I think I actually have slides on all these as I look at it. Yeah, let's talk about this. So how oval an orbit is called the eccentricity. Okay, so it's also just known as E, and so it's for eccentricity. Trying this with my computer. So an E value is always going to be less than 1 and greater than 0. This is the eccentricity. 0 means circular. And 1 is not an orbit at all. It's actually an escape orbit like this. And anything in between is a circle. So 0.9 is a very elliptical orbit. This is like for comets and stuff. For your reference, in our solar system, no planet has more than like a 0.1 eccentricity except for Mercury. Mercury is an odd duck. It has a 0.2 eccentricity, and even then it's not very eccentric. Like, it's not very oval-like. It's very hard to have stable solar systems when you have high eccentricities, especially ones that have life, because if you're here, it's going to be super hot, and if you're here, it's going to be super cold. And then there's also odds of other planets crossing through your orbit, so their gravity is going to destabilize you, and you'll get slung out of the solar system, or vice versa, or you'll collide. So it's very hard to have stable worlds that are stable long enough for 4 billion years of life to emerge if you have a very eccentric orbit. That's why you look in our solar system and there's like hardly any certain very eccentric planets, because we couldn't have had and stayed stable. Retrograde orbits. So all the planets in a solar system, because they form from the same stuff, they all generally orbit in the same direction. Okay, if they all form there. If you have a planet that's doing the opposite, it did not form in that solar system. So you could have captured worlds that are orbiting in the opposite direction that the sun is spinning, because all the planets, not only are they moving this way, they're also spinning in the same way. So is the sun. They all spin and rotate in the same way because they formed from the same stuff, and they have their and to change them would have required a big change in angular momentum. So any planet that's orbiting this way, something happened. It was probably captured. It was a rogue planet that got slung out by another world that had an eccentric orbit or something, and then was captured later by another star. Now, the spin, though, could be the other way. Like, you could have a planet that spins this way, even if it orbits the right way. Venus does this, by the way. So our own planet Venus is spinning opposite what all the other planets spin. So something has to explain that, like what happened. In Venus's case, it got pummeled by asteroids. And that's why it spins the wrong way. Okay, so here's some other ideas of like binary planets. Here's some descriptions of the weird ones. So here's a binary planet in a solar system. They're orbiting each other. They probably wouldn't orbit this close. But the fact that they are, you can see they're naming the planet Roche World. Do you understand why? Look how close they are. They're going to be inside the Roche limit. So and that's why the planets are stretching like this. That's why they call them Roche World. So that'd be kind of a cool world. You can see how the air and the water kind of flows from one to the other, it looks like. That's kind of weird. Might be a fun sci-fi book to read. They probably aren't that close if they're truly a binary planet. Here is the 5 Lagrange points where you could have orbits that match on the same orbital line. And Jupiter actually has asteroids at the 5 and 4 points. There is an asteroid belt between us and Jupiter, but then there's also pockets of asteroids, and they're called Trojans. Ouch. So yeah, being on a Lagrange point is being known as a Trojan object. So Jupiter has Trojan asteroids here, here, and here, I believe. So but it'd be kind of cool to have worlds at the 3 and the 2, or the 4 and the 2, and they would be linked. So we're going to have a system. We're going to have a mission called High Ground, where there are planets on these points right here. Let's see. This is a tadpole orbit. Yeah. They kind of orbit the star, and the orbits cross like this. And because they cross, they kind of pull each other off. So the idea is that this world and this world get closer together over time. So you see how he's kind of... Oh, it's kind of odd. Here's what it is. So you have a world here. Here's like Earth. And then you have another world here, and it spins... It orbits like nothing here as it orbits the sun. And this little spin that it does gets far away and then comes close again. Far away and comes close again. Far away and comes close. As the gravity of these objects kind of destabilize. As it gets... Yeah, so that's what it's doing here. It's going in a circle, but it's getting close and then far away and then close and far away. That's a tadpole orbit. This is another example of a possible tadpole orbit. And because of resonance, they'll never hit each other. Anyway. Yeah, so these two are kind of this... Ouch. Oh, no. What this is showing here is how this thing is going in a circle like this, but the circle's also orbiting the star as the Earth goes around the star. But then this circle keeps getting further and further from the Earth as they move, and then it gets closer and closer again. So that's kind of a tadpole planet. The quasi-satellite is something like this. They are both orbiting the sun about the same distance away. Okay, However, because they are constantly pushing on each other, from the blue planet's perspective, the pink one is kind of orbiting around it, getting closer and further away. But it's not like a moon. Like a moon would be spinning around the planet like this. That's what a moon would do. You see how it's not really doing that. That's why it's called a quasi-satellite. So there's a bunch of weird orbits that you can do. If you want planets that are on the same distance from the sun and not hit each other, you're going to have to choose like a Trojan, a tadpole, or a quasi-satellite. And you may have to do that if you want life to evolve on these worlds, because your Goldilocks zone where life can evolve may be too small to have, if you need 2 planets in the Goldilocks zone, they'll be too close to be a regular orbit. Okay. All right. Now, I think that about covers the types of stars, the characteristics of the stars, and so we can kind of sum up now. And if you want to come back to this again and again and review, we'll kind of summarize it here, and you can just skip here. Okay, so there's the star types. Let's make a bigger thing so it's easy to read this. So you're going to start with your star type, and you've got the O, B, A, F, G, M, and K, and then M. Okay? So, and the ideas are so color is tied to type. So the O's are going to be blue, O and B are blue, A's are like white, F is white turning into yellow, G's are mostly white, a little bit yellow, and then the orange and the red. And that's also the temperature. Okay? Now, the bigger the star, the sooner it dies. And that's why you mostly have M stars and have very few of these, because these die off quickly and these stay forever. Okay? So O and B can't have planets. They die too soon. And you need to have F, G, K for life. Okay? The reason is that these are the ones that they're stable long enough for life to evolve, especially the Ks. Scientists think maybe K is the most ideal for life. F, you have to be on like the cool end of it. So that's for life. And then you have the planet types. You've got rocky, gas, and then you've got ice giants. Okay? And then you have the orbit lines. So that's the Roche limit, where you get ripped apart by tides. You have the rock limit, any closer and your rocks melt. You have the ice limit, where ice turns to water. Then you have the hydrocarbon limit, and this is where like methane and other carbon chains will melt inside of this. And then you also have tidal lines. So if you're too close, then you'll have a tidal. So then we might have orbit types. So you could have the orbit types, like you may have a weird one. So weird co-orbits, and there's a bunch of types in there, where you have the tadpoles, you had the resonant, you had the semi-satellite, and you had the Lagrange. Okay? And then beyond that, you had just regular elliptical, with your apoapsis is the close point, and the the periapsis is the close point. The apoapsis is the far point, and the eccentricity says how elliptical it is. And then you had the tidal orbits, where you were so close that the planet always points in the same direction as the star. So you can kind of play with these as far as life goes, or as you design your planets. Now, as we get into how to design these planets, you really don't have to worry too much about these. You don't have to choose them, that is, because on the spreadsheet of the worlds that we're adding in, the classes are actually already known. These are because our spreadsheet of stars are all actual stars. They're the real stars. So the classes are already known, but you need to know the types so that you can decide, okay, if I choose this system, what could I expect to find there? And that's when you start to get down here. Because the thing about these systems is we may know what the star is like. We don't know anything about worlds there. Our telescopes haven't found them. It's really hard to find planets. So you get to be creative then. But you need to know the boundaries, specifically like where you would have planets at all, where you might find life, and then where to place your orbits. Okay? And then the next video, I'm going to go over the actual orbit spreadsheet. So that's how we're going to check things like the hill radius. Remember, you got to worry about hill radius to know if you're too close or not. Okay. That's the end of this video.